let's first look at that question which we did not solve yesterday. So, that same question sheet. So, minimum vertex cover, there was another algorithm given, right? And algorithm is given to you. So, you have to show that it actually finds a minimum, it finds a vertex cover of the graph, right? That is, it's a feasible solution that you need to show. And the second thing that you need to show is that it gives a good approximation. So, it is not very, its size is not too high compared to the minimum vertex cover of any given graph, if you run that algorithm on the graph. So, what is the, so anyone got the solution? So, you need to, you got it. So, I will ask you to prove step by step, so you can do that. So, the algorithm given is this: find a, assume that the graph is connected, because if it is not connected, you can solve this problem for all the different connected components and take the union, and that is sufficient. So, without loss of generality, let us assume that the graph is connected. So, find a DFS tree of the input graph. Say T, okay, and S is the set of all non-leaf vertices of T, okay. So, return or output S. So, this is your solution. So, we need to show two things here. One is that S is indeed a vertex cover of the given graph. So, okay. S is a vertex cover of not T, but G, right? The given graph is what we want to find vertex cover for, not T, right? That you need to show, okay. The second thing that you need to show is size of S is less than or equal to 2 times the vertex cover of G, okay. These two things we need to show. So, can someone show, maybe you can show? Okay, anybody who wants to show why S is a vertex cover, or you can tell me the steps, I will fill it up. Why S is a vertex cover? The algorithm is clear, no? Everybody have heard of DFS? Okay. So, DFS will give you a tree for a connected graph, right, wherever, because everything is connected. So, take all the internal vertices of the DFS tree. It is a vertex cover of the graph, is the claim of the graph G, not the tree T. Why is it true?
Suppose assume that S is not a vertex cover, then there should exist a vertex among the leaf node, there should exist an edge in between leaf nodes of the DFS tree.
Because all vertices are present in the DFS tree, all vertices of G are present in the DFS tree, right. So, as he told, then if at all this set of internal nodes is not covering every edge of the graph, then in the graph there should have been some edge in between two leaf nodes, okay. So, let us try to prove one. then there is some edge whose both endpoints are leaf nodes, right? Is there any problem with this? It is a DFS tree. So
if both are from leaves, then the obtained tree is not actually a DFS result because it should go along the depth first. So one of the path should have been extended along the DFS. So that is not a DFS tree, which is a contradiction.
So he is telling me that there cannot be, if you take any DFS tree, such an edge between, in the original graph, there cannot be an edge between two leaf nodes there, okay. According to this tree, whichever is a leaf, there are two leaf nodes, there cannot be an edge between them. The reason which he is telling me is that, so DFS is a depth first search. So if at all there is a, so you would have gone in this DFS tree in some way, you reach some leaf node, okay, somewhere, okay. From this leaf node, suppose this L1 is a leaf node and L2 is some other leaf node through some other path. Suppose there was an edge between these two, then this is not in your DFS tree, but this is in your DFS tree. How is that possible? Because when we reach this L1, L2 is another neighbor, okay. So before you go back from L1, all the unvisited neighbors of L1 will actually come in the subtree that is here. L2 would have been somewhere below L1, okay. So it is a property of a DFS tree that in the original graph, all the leaves, they form an independent set, right. Okay. So this is not possible. Because T is a DFS tree, okay. Either L1 will be below L2 in its subtree, or if you found L2 first, then L1 will come below that, okay. So this means that, okay, what does this mean? That S is indeed a vertex cover, right? We got a contradiction, right? This is not possible. So the conclusion is that S is a vertex cover of G. Now the second part.
The second part, the DFS tree is basically a subgraph of the bigger graph. Alright. So now if I, the vertex cover, the S is also happens to be a vertex cover of the DFS tree.
Correct.
Yeah. So we know that the property that the any vertex cover of a graph is less than 2 times the minimum vertex cover of the same graph.
Any
vertex cover of a given graph is less than 2 times the minimum vertex cover of the same graph.
Obviously.
Yeah. So now.
Why? I mean, you need to reason out why.
We proved yesterday.
What?
That
we did not say any vertex cover, no? If you want to argue that, you need to argue further.
Yeah, like for a tree, for the tree, the vertex cover size happens to be n like number of vertices by 2, I guess.
No.
For a tree, it happens.
No, right? Because you take a tree in which there is one center and there are all leaves, then its vertex cover is only 1, right? This graph. The vertex cover is only this. It's much less than. But we had an argument related to matchings, right? You can relate it to matchings. Yesterday we had a relation, two-sided relation, relating vertex cover and matchings, right? Maximal matchings. So can you think, there is a hint given in the question. Please look at it and think for some time and let's see. First explain to me what is the meaning of that. How that can be used. Then we will worry about how to obtain such a matching. Okay. Suppose you obtain a matching that saturates all the internal nodes. Saturates means it matches all the internal nodes. Suppose G has a matching in which all internal nodes of T, say matching M, okay, are matched. Then can you make the conclusion? So, see here I do not know if this is true or not. I need to show that there is such a matching, but suppose I, for the moment, just suppose that we know that there is such a matching in which all the internal nodes of T are matched. Okay. Then can we argue that, so this original S set of all internal nodes is at most 2 times the minimum vertex cover number of G. So, is that, for that you will need only what that relation which we derived yesterday, the two-way relation. Just show me how to. That we cannot say because the tree may be very broad, right. So, there may be multiple, right. You have drawn only two children.
This we can't take.
See, so then you have this, no? From everywhere you can have.
Yeah.
Just relate. So, okay, suppose you are given one matching which is not maximal. M may not be maximal, as I have written, this M may not be maximal, right. Is there a way to extend it to get a maximal matching? Can we, if you are given an arbitrary matching M in G which is not maximal, can you make it maximal by adding some more edges? How will you do that? You did something starting from null set yesterday. So, what do you do? Okay. So, the first question is, can we obtain a maximal matching M dash by extending M? Is it possible? Suppose you are given a matching, right? It is not maximal, that means there are some, it can be extended further, right? That is the meaning. That is why it is not maximal. Maximal is not about cardinality, maximal is about it cannot be extended further, right? So, how do you find another maximal matching in which all edges of M are already present? I mean, it is obvious, tell me how to. You are given a matching. If it is not maximal, how will you make it maximal? By adding more edges. Well, how? Which edges will you add? Okay. And then? Okay. So, she is telling me a way to add one more edge to M. So, the first thing that you can do is look at all the edges that are not in M. If at all any of them is such that none of its endpoints are incident on any of the matched edges, matched vertices, then pick that edge and add it to M. Okay. So, you have expanded M by 1. If it is still not maximal, you continue this, right?
Isn't this matching maximal?
This matching is a maximal matching.
It's, I do not know. it is a, then you need more arguments. In G.
It is in G, the
Leaves, which is not there.
not there.
Correct. So, what he told is, actually this M itself, which I defined like this, right, this is a maximal matching. That is actually true. M is a matching, suppose M is a matching in which all internal nodes of T are matched, then that is a maximal matching is what he is telling me. That is actually true. One observation is that M is a maximal matching in G, not in T but also in G, because every other edge, if you try to take any other edge of G and try to add it to this matching in which all the internal nodes are already matched, then anyway, because there are no edges between the leaves, nothing can be added. So, M is a maximal matching. So, M is a maximal matching in G. Then can you now tell me that S, what is the size of S then? M is a matching. I did not say no other vertices are matched. I am saying all the internal nodes are matched, some more vertices may be matched, right? I mean some more, yeah. So, what can I say about the size of S? Can I conclude this? What can you give me a lower bound on the size of the matching? Can you say that size of M is greater than or equal to something? Do you agree? Size of M is greater than or equal to S by 2. Number of edges, M is counting edges. Because all the internal nodes are matched, everything has one matched partner. There may be some more vertices matched, who knows, some leaves also may be there in the matching, right? Maybe, correct. So, M is greater than or equal to S by 2, right? Because the set of matched vertices include everything in S, right? Correct? So, everyone agrees with this? If not, ask me. If you have say k edges in a matching, okay. Say if there are T vertices matched by M, okay, then actually M is equal to T by 2, right? I mean T is equal to M by 2. No, the other way. M is equal to T by 2, right? If you have a matching in which exactly T vertices are matched, what is the size of the matching? Number of vertices by 2, right? Fine. Now, this is a matching in which all internal nodes are matched. Some more may be matched. So, the T here is greater than or equal to cardinality of S, right? So, T, number of vertices matched, T is greater than or equal to S, because all internal nodes are matched, cardinality of S, okay. So, that is why I can say that M is greater than or equal to S by 2, right? Everybody with me? It is a simple argument, right? You have all internal nodes matched. So, the size of matching is at least S by 2, correct? Fine. It can be more, but it is never less than S by 2, right? Now can you tell me why it is less than 2 times vertex cover of G? M is a maximal matching, right? Correct. So what we know is cardinality of M is less than or equal to, or vertex cover of G, right? So that means so this also means that 2M is greater than or equal to S, right? And this will give us 2M is less than or equal to, okay, S is less than or equal to 2 times the cardinality of maximal matching, and which is less than or equal to, right? You agree with this? I am only using what we did yesterday, that given any matching, we know that vertex cover has to be at least the size of the matching. Any matching, it need not be even maximal, okay? So because we know this, we can conclude this, right? So if we get a matching M in which all internal nodes of the DFS tree are matched, then we are done, right? Then we have proved that the internal nodes, set of internal nodes will form a vertex cover, and it is of size at most 2 times the optimum value. Vertex cover of G is the optimum value of vertex cover on this graph, right? Okay. So now what is the problem left? Find a matching in G in which all internal nodes of T are matched. So, okay. So how will we find it out? So a matching in T is also a matching in G, right? Right? Is it so? It is, right? So my question, I told, if suppose G has a matching M in which all this is matched. So I can actually ask you one question. Can you now find a matching in T itself? Okay? Such that all internal nodes of T are matched. The same matching will be a matching in G as well. Why? Because none of the edges, what is the definition of a matching? None of these edges share a common endpoint. If that is the case in this T, that is the case in G also, right? So such a matching will suffice. So now your question is, can you find such a matching from a tree? Given a tree, just draw some trees and tell me an algorithmic method in which you can find a matching in which all internal nodes are matched. Just give me an algorithm. I think that may end up with some problem.
Because if you need the internal vertices, right? You need the internal vertices, the internal nodes, alright? What do? You take the support vertex.
So finally, where will the root get matched?
Now it will be a smaller version, right? So for small hypothesis, we will have it. What I'm doing, I'm including the support vertex and the joining the pendant vertex and the supporting vertex. I'm taking that edge and including in my matching.
Okay.
Alright. And now what I'm doing?
Once again.
I have the support vertex and the leaf. Alright. I take this edge. Alright. And I delete the support vertex.
And this edge, I mean this vertex both.
Yeah. Now I have a smaller version of the tree. Now I can go ahead and inductively put it. Because if it exists for this, then by hypothesis,
see, the problem here is that you are trying to match, in fact, all leaves, isn't it?
No,
you unroll your induction and see. You are trying to match all leaves now, right?
See, what will happen, like when the supporting vertex is also an internal node. So if I take that edge,
I think that will not work. See, the problem is that you are now trying to say that this is matched with this, right? Right? So you are matching this and this. Maybe you have something here, you have something hanging here also, right? Right? In your tree. Then you are saying by inductive hypothesis, you have a smaller tree in which you will find a matching in which all internal nodes are matched, but this is not an internal node probably in the remaining tree. It may be an intermediate, it may become a leaf once you delete this part, right? So how will you match this one? See, there is no other child for this. Maybe it is like this, okay? Then if you delete this, then your inductive hypothesis does not tell you that this vertex is matched because it is a leaf in the tree from which you delete these two, right?
I deleted that.
Correct. What is your assumption, inductive assumption? That you can find a matching in which all internal nodes are matched. All internal nodes are matched, but of the smaller tree. But that vertex is not a internal vertex of the smaller tree. It is a leaf. So this strategy will not work. It may not work.
You only delete the leaf. Don't delete the support vertex, you only delete the leaf.
Then I cannot match it again, right? It is already matched. I am not supposed to have one more edge which is adjacent to this. Refine your strategy. That strategy will not work. You got the problem. He was telling me that maybe we will try by induction. Take one leaf node, match it with its parent. It has one parent anyway, right? Match it with that. Suppose the graph has at least 2 or more vertices. Match it with its parent. Then delete both these things and try to recursively find a solution for the smaller tree and do it. But then the problem is, what will you assume as induction hypothesis on the smaller tree? That you can find a matching in the smaller tree in which all internal vertices of the smaller tree are matched, right? But now you may not match all the vertices of whatever was an internal vertex of the original tree may not be an internal vertex of the tree from which you delete this part, because that may not have any other children, right? So that strategy will not work. So, but there are better, algorithmic constructive techniques in which you can do it. Just try it out. If you try, you will get.
Time of entering and time of leaving a disjointed DFS, you can consider only those cases.
You don't need to actually think of DFS also. Any tree, this is true. Any tree. It need not be a DFS tree.
While arguing the induction hypothesis, we will take base cases. So this case would be included in base case itself, where there are 3 vertices and 2 edges joined.
No, this may be more, no. I am talking about induction hypothesis, you have to apply on this tree. This is not a base case, this is a very big tree. Right, that strategy will not work. Because actually if you unroll this induction, what he is doing is matching all leaves, not actually matching all, right. He always will match all leaves, but that is not what we want. We want to match all internal vertices.
Suppose that in which all internal nodes of that DFS tree are matched. What is that nodes matching?
Nodes match means if it is an endpoint of a matched edge, we will say that it is matched.
At least one, if that node comes in
Correct.
any of the edges?
Correct. That's a matched vertex. You can use some other type of induction if you want to, recursion, induction, anything.
We start from root and we select one edge. And then you delete these two vertices and this side. Then we can select the next subtree and connect this.
What about this, whatever is remaining here? There may be some other things hanging here, no?
This is leaf. If the subtrees, that subtrees also we will consider same.
So this vertex is gone. This vertex is gone.
These two vertices are gone.
Now these edges are also gone.
This becomes a subtree and then we can.
Correct. So in this way, all those things are matched, right?
Subtree continues if matches the leaf.
Correct. You don't need to. Sometimes it may get matched. Then include it. Otherwise, remove.
Okay, then we have internal nodes covered with every vertex will be covered by
Correct.
2 matching. So
Every vertex,
every internal nodes.
you have to find a matching such that it covers all internal nodes. You have to find it.
Okay, internal nodes. That's it. These 2 edges will cover all the internal nodes.
In this graph, no. I am saying given any tree, you need to give me a strategy. Given any tree, not this tree. See, don't tell me this graph and that graph.
Okay.
You have to give me a strategy that will work for any given tree. Right? I told you yesterday also, don't tell that it will work for this particular tree and this particular tree. I can give you another tree, it should work for that also. Strategy should be such that it will work for everything. Right? Yeah, but I think you have some idea. If you try to make it formal, then it will work. I'll give you a hint. Try to match the root first. Okay, one hint, you can try to match the root first. Somebody has found the solution, I am giving you their hint that try to match the root first. Huh? From the leaf side, you may be able to have a very complicated induction, but that induction which he told will not work.
Suppose for less than we will argue on the number of vertex. Suppose T is a DFS of G. Okay. And it has a leaves. Suppose this is a leaf.
That it can have many leaves.
Take one leaf. This is V1 and V2. This is the leaf. Now we delete this vertex and consider the whole other DFS.
But the problem then is that maybe for matching this vertex, you will need this one.
I'm telling the argument.
Okay.
So this is a DFS, a smaller, so it has a matching, which match all the internal vertex. Okay. So for that,
this may or may not get matched.
Then we will include this edge, either we will include this edge. Suppose then this is the internal vertex of this, and this is the leaf. So by the argument, this will have a matching, which match all the internal vertex, and this vertex will get matched to it. So we consider it may have some branching. Suppose. So it may be matched by in three different ways, either this edge, or this edge. If these two edges are chosen, then we will choose this edge. We will incorporate in the previous matching. If this edge is chosen, then we are ultimately done.
That works. That works. Okay, now I got two solutions. Essentially both are the same, okay, but two solutions I got. Anybody else? Okay, so there are several methods to do it. So one method that is very easy that somebody has told me is this, that suppose it's considered as a rooted tree, one root is there, right? At least two, suppose there are at least two nodes in the tree, otherwise we are done, everything is matched, right? There is no internal node in that case. So if there is something like this, right? So suppose you want to match all the internal nodes. First let us match this root. Let's match it with its leftmost child. Okay. So this vertex is matched now, right? This vertex is also matched. Okay. This, if at all it is a leaf, it's okay. That also gets matched. Okay. Anyway, this internal node is matched. If at all this was an internal node, that's also matched. Now you delete both these vertices from the graph. So that will delete these edges from the graph. Okay. Let me, okay. So, okay. Now you can do the same thing. If at all there is a subtree here, you can do that here. You can do that here. I mean, not here. Right. When you delete these two vertices, you will get several pieces. Right. In all these things, you can do the same thing. And this process will match all the internal nodes of the original tree. Right. Each time you will be matching the root. Okay. So that is the easy method. Then somebody else also told me another way in which it is done bottom up as he was trying, but his method is not to fix this thing. So he has got a tree like this. Okay. He takes the leftmost branch, okay, and takes this edge, leftmost edge like this, okay, he will not fix the matching right now. He is telling me right now you don't delete both these vertices, but just delete this vertex for the time being, okay. And you inductively solve the problem on this graph. So, that will find a matching on the other graph in which all the internal nodes of that graph are matched, okay. So, it can happen in two ways. So, either this parent of this one is a leaf in the smaller tree, or it is an internal node in the smaller tree. If it is an internal node in the smaller tree, that matching itself will do, right, matching that you found in the smaller tree itself will do. If this was not, if this was a leaf in the smaller tree, there are two possibilities, either this got matched or this did not get matched. If it got matched, you are still okay, right, it will be a matched vertex in the resultant graph also, right. It is an internal node, still it is okay, it is matched. If it is not matched by the matching that you found here, because inductively you could not get it, right, induction does not guarantee that. If at all it did not, that matching that you found there did not match this vertex, you match it with this, you include this edge also in the matching in that case, okay. So, that is also another way to do it. So, there are many ways to do it. So, what did we achieve finally? So, the answer is that yes, there is an algorithmic way. Right. So, to sum it up, our strategy, this was all proof only, right, everything is a proof only. My algorithm is this, back to this, come back to this. Now, just find a DFS tree and output all the internal nodes of the DFS tree. It will be a vertex cover. We also showed that it satisfies both these conditions. It is a vertex cover and it is at most of size 2 times the minimum vertex cover of G. That is what we have achieved. Everything else what we did was a proof of that claim. Okay. Okay. So, this is another method. So, using the same lower bound, which is that a matching, if you have a matching M, then vertex cover is of size at least M, cardinality of M. That lower bound is what is helping us in this algorithm also to bound. I mean, it is not required for the algorithm, but it is what is helping us to bound the size, that it is at most of size 2 times vertex cover of G, right. Okay, that relation with the related problem. Related problem is matching. Fine. Any questions? Okay. So, okay. So, now let me move on to a related problem, but it is instead of this we want to find the minimum cardinality set which covers all edges, set of vertices that covers all edges. I want to make the problem slightly more general, I have a minimum cost vertex cover, minimum cost vertex cover. Okay. So, here I am given a graph input, a graph G in which every vertex has a cost. Okay. So, we have a cost associated with every vertex, and the cost, let us assume that it is a positive rational number. Okay. And then your task, aim, objective is to find a vertex cover of G of minimum cost. Okay. That is, the total cost of vertices in your vertex cover is the minimum. Okay. So, it should be a vertex cover, not only that it is a vertex cover, okay, we do not know, we are not saying it should be of minimum cardinality, okay, but we are saying that it should have minimum total cost. Okay. Maybe if you take some more vertices, your cost will come down and it will still cover all the edges, cost will come down, but cardinality will increase, it can happen in some cases. Okay. So, this is your problem now. So, it is not obvious how to use our previous strategy for this, because maximum matching size may not obviously give a lower bound for the cost. Now, our objective function is the total cost. One constraint is that it should cover all the edges. The set of vertices should cover all the edges, that is our constraint, right. Objective function is not the number of vertices, but it is the total cost of the chosen vertices, correct. So, you have probably written one integer linear program, right, for this integer linear program. That was one exercise question. If you have not done it, we will do it. Okay. So, we will get a two-factor approximation algorithm for minimum cost vertex cover. This is a generalization. So, this will work even for the normal vertex cover also. This will work in particular even if the costs are not unit cost. It can be other costs also, right. Okay. So, two-factor approximation algorithm for minimum cost vertex cover using linear programs. So, the method is this. So, first formulate the given problem as an integer linear program. Okay. What is an integer linear program? A linear program in which you have an objective function which is linear, right. Objective function is usually of the form say C1 x1 plus C2 x2 plus etc. plus Cn xn. So, you can say minimize or maximize. So, minimize this thing, some linear function. These coefficients are
like weights.
no, in a general integer linear program also these coefficients can be rationals, okay, or real numbers. Okay. So, each Ci R, in our case, okay, it will be Q plus, okay, and constraints. So, we will write subject to some A11 x1 plus A12 x2 plus etc. plus A1n xn is greater than or equal to some B1 etc. right. So, and then we have the usual constraints here. This is a standard form. Okay. Huh? Okay. And what about these coefficients? What are they? If it is an integer linear program, then we will have all of them as integers, and not necessarily. The solution need to be integer. So, all the Aij's are in R and all the Bj's, right, are also in R. So, this is the general form, and if it is an ILP, we are actually only restricting the solution space. This looks like an LP, right now. What is an LP? Well, that is what is given. You have a linear objective function and you have a set of linear constraints and you want to optimize. This is an LP. Here I want to find this tuple x1, x2 to xn which belong to, all of them are, if I allow them to be reals, if I allow them to be reals, then it is a general LP. If I allow them to be only integers, then it is an ILP. Okay. Okay. It is an LP, and if okay, Rn, it is a tuple, right, Rn. If this is Zn, which is integers, then it is called an ILP. That is, if it is an ILP, then you are supposed to always return me a solution in which all xi's are integers. Whereas, if I allow you to give me any LP solution, then you can even give me values like x1 equal to 1.5, x1 equal to 0.5, x2 equal to 0.5, etc., which is not allowed if I make the constraint, additional constraint that I want solution in which all xi's are integers, right. Now, have you already seen that integer linear programs in general are NP hard to solve? NP or okay. Have you seen how to write? Can you? Okay, let us now try to write minimum cost vertex cover problem as an ILP, integer linear program. You write. You have to decide what are the variables, what are the constraints, and what is the objective function. Okay, an ILP such that if you solve the ILP, the optimum solution the optimum integer solution, I mean the, it is not the, any of the optimum integer solutions will correspond to a minimum cost vertex cover of the given graph. So, from the graph how will you construct this corresponding ILP? Just try. I think you have done it. Yes. So, what is the, let's have one variable corresponding to every vertex. That is typically how we look at it. One vertex or one edge, or say if it is a set cover, one set, okay, things like that. So, let xi correspond to set, I mean vertex vi for every I. Now, try to write it. Okay. For each vertex have a variable. So, what should be our objective function? Objective function, that similar, same thing that I, right? Every vertex has a cost. Okay. So, this variable, the interpretation is this way. This variable will be set to 1 if it is included in our vertex cover. It will be set to 0 if it is not included in our vertex cover, okay, in the solution. So, xi is 1 if vi is chosen in the solution, 0 if otherwise. Okay. So, the total cost of all the selected vertices is what we try to optimize. So, that will be sum of Cixi, right. So, our LP, that is very simple. So, we want the same thing only, minimize let us call it n, okay, n vertices, usually that is the way we take it. So, that same thing, this is our objective function. We want to minimize the sum of costs of all the selected vertices, right. For non-selected vertices anyway the term will be 0 because we are assigning cost 0, fine. So, what are the constraints? What is the constraint?
Summation ai's x size is greater than 1. जो vertex is included in the vertex cover with some.
If you think about the vertex cover, this problem, right, what I stated, what is the constraint? Don't tell me the constraint in terms of this inequalities, but what is the constraint? What are the constraints of this problem? It should be a vertex cover, or in other words, the chosen vertices should form a vertex cover. That is, every edge should be covered by the selected vertices. So, how will you express that?
Endpoints, by the endpoints of the edges, xi and xj are the endpoints of an edge, xi plus xj greater than equal to 2.
2 means both should be selected, no?
Greater than equal to 1.
Right? Okay. So, you look at any edge, every edge has to be covered by the selected vertices, right. So, the constraints are, there are, if the number of edges in this graph is m, there are m constraints, okay. One constraint corresponding to each edge. So, consider an edge E from Vi to Vj. What is the corresponding constraint? So, he told me that for every edge, at least one of its endpoints should be selected. That is a constraint, right? So, I should have, it is a linear constraint. So, I should write it as a linear inequality, right? Xi plus Xj.
Is greater than equals to 1. Either this is
correct. Greater than or equal to 1. This means that both cannot be 0, right? At least one should be 1. Both can be 1, then also it is satisfied, it is okay, right? Now, I also will, because it is an integer program, I will also say that xi belong to z. Actually, I told that it is actually 0 and 1, right? It is already there for every I. Okay. So, this is our integer linear program. See, this is a way of representing minimum vertex cover program as an integer linear program. So, what can you say about the complexity of solving integer linear programs? Is it easy? Can you solve integer linear programs in polynomial time? Suppose you could solve all integer linear programs in polynomial time. Polynomial time in the size of what? The number of variables, the number of constraints, all that. Okay. Then vertex cover can be solved in polynomial time, right? Which is NP complete, so we don't. That is not likely, right, unless P is equal to NP. So, that means integer linear programming in general is an NP complete program. Okay. Is NP hard, but then you can also show that it is in NP, because given a solution you can easily verify whether it satisfies all the constraints, right. So, it is in NP also, right, substitute and find out, right, whether it satisfies all the constraints. So, this shows two things. One is that when I am saying NP complete, the corresponding decision problem is NP complete. Does this integer linear program has a solution which has objective function value less than or equal to something, k. That is the decision problem, corresponding decision problem, okay. That is NP complete. So, this shows that ILP decision problem, that is given this thing and a target objective function value, whether it is less than or equal to that for a minimization, for maximization greater than or equal to that value, that is NP hard, actually NP complete. Okay. But then the nice thing, I am not going to prove it, it is well known and it is a classical theorem that if you are allowing instead of integer solutions, you also allow all real valued solutions. Okay. You are allowed to get vectors of Rn, not just Zn. You do not restrict them to be integer solutions, but allow any real solution. Then that is in P. That can be done in polynomial time. In fact, you have many solvers available in the internet, which if you give LP will give its solution, real solution, not integer solution, real vector solution. Okay. So, the fact which we are going to use for getting this kind of approximation algorithms is that, but it is well known that finding an optimum solution of a general LP. It's not ILP, LP. If you don't have the restriction to be integers, can be done in polynomial time. There are many methods. Okay. So, one of the algorithms is by a person called Kachian. So, there are many methods. Okay. So, from now on we will just use this algorithm as a black box. Okay. That is like we assume that if we had no restriction of being integer solutions, we will get the solution very fast, quickly, efficiently. It can be done in polynomial time. From that solution, we will construct an integer solution. Okay. So, for doing this, solving this problem, the related problem that I am identifying is the corresponding LP relaxation. I call it LP relaxation if I replace this constraint, right, by allowing that all xi's can be in R, not necessarily in Z. Okay. If I convert a given ILP to an LP by removing the constraint that variables should be integers, okay, that LP is called the LP relaxation of the ILP given. Okay. LP relaxation. So, that means I will now remove this. Okay. I will now remove this also, and I will allow xi is greater than or equal to 0 for all I, and xi is a real number. This is what I allow. Okay. Not necessarily in Z. So, this is solvable in polynomial time very efficiently. This small conversion makes it easy. Okay. Okay, now our related problem is defined, which is easy to solve. But suppose you solve this related problem. Now, how will you relate the solution of the related problem? From that, you need to construct a solution for our problem. We do not want these fractional values and all. We want only xi's to be 0 and 1 finally, so that we can interpret it as a vertex cover, right? Okay. So, suppose by solving this LP, you got a solution in which some values are say 0.5, 0.3, 0.2, 0.8, things like that. Okay. You got a solution. How can you convert this to an integer solution? Some kind of rounding we will do. Okay. So, what kind of rounding should we do? Seal. Okay. So, seal, that is one rounding possible, but the problem is that I need to argue about, there are two things. Okay. So, the second step is obtain the LP relaxation and solve it. In polynomial time we can solve it. Now third step is to convert the real valued solution to an integer valued solution without increasing the cost much. I cannot do it without increasing the cost at all. I do not want to actually increase it more than the cost of the linear programming solution. So, what is the relation between I had one ILP, I had the corresponding LP relaxation which is now there on the board, right. What can you say about the optimum value of these two? How do they compare? Which is smaller? Which can be, I mean, what is the relation between them? I have one ILP, I have the corresponding LP also. It is a minimization problem. So, which one will give better solutions? LP. Why? Any ILP solution is also an LP solution. So, we are likely to get better if we also allow real, right. We are not losing anything. So, what we know is this. If we have let us call this as an instance. So, opt LP of I, this is a minimization problem, that is why it is like that. If it is maximization, it is the other way, right. So, this will be less than or equal to, if you allow only ILP, it may not get that minimized, okay. So, this is for minimization problems. Okay. So, suppose I got a solution, okay, and I am trying to, maybe some xi is 0.1, some x1 is 0.1, say x2 is 0.9, there is an edge between them, so it should be at least 1, right, and say x3 is like this, there are some values that you are getting, suppose that is the solution. And somebody told, and maybe something else is a x5 is 0, this is a solution, okay, such that all constraints are satisfied. If you round this, just round it by taking ceil, what will happen to the cost? So, I am saying if xi is 0.1, let me make xi 1. Right, xi dash, let me define x1 dash to be 1, x2 dash to be 1, x3 dash to be 1, etc. x5 remains 0 because it was 0. Anything which is 0 remains 0, other things, okay. One observation is that I do not need to give any values which are greater than 1, right. That is obvious from this formulation, because by giving 1 itself I will satisfy the constraint, then why should I give a value which is more than 1, right. So, though I have not written that xi is less than or equal to 1, that is automatically forced for any optimal solution, right. If I am increasing the value of xi, costs are all positive, right. My objective function is this thing, Okay. If I have something which is greater than 1, I should satisfy, I could have satisfied the constraint by making it 1 also, right? Any constraint, right? The corresponding constraint can be satisfied by making it 1 also. Then the cost will be better if I make it 1, right? Because all Ci's are positive, I can say all these things. By making any value bigger than 1 to 1, I am gaining, right? So, there is an unseen thing that is coming here, that though we do not say it, for any good solution, any optimal solution, xi will be less than or equal to 1 for all I. Okay? That is guaranteed. Now, if I do this kind of a conversion, right, I round them up, then what can I say? How will the cost, what will the effect on the objective function value? You cannot really say, because you are rounding up 0.1 also to 1, right? That rounding is too much, I mean rounding cost is too much, right? Here, okay, so you do not get, that is not a good rounding. So, what is a better rounding? Ceiling we should not do, okay. So, okay, if you do ceiling, 0.1 becomes 1, which is like a 10 factor increase, right. If all the variables are increased by 10 factors, then this thing will also become more by 10 factor, okay. What I am trying to do is, okay, I have this relation, I am trying to show that one solution that I am going to get is less than or equal to 2 times the optimum value of LP. Anyway, I know that LP value is a lower bound. I am trying to get an integer solution whose value is at most 2 times LP solution value, which is like the lower bound, right. So, it is within 2 factor of the best possible, that is my objective. So, because I am aiming for the 2 factor, now do you see a better rounding? Okay. So, because it is 2 factor, right, which I am aiming, I have that in mind, okay. And also looking at this one, because it has only 2 variables, right, it gives me a clue that, let me try to say that anything which has value greater than or equal to 0.5, I will round to 1. Anything less than 0.5, I will round to 0, okay. So, let us forget about this bounding. Okay, xi dash becomes 1 if xi is greater than or equal to 0.5, it becomes 0 if it is less than 0.5. Okay. Will it be a right solution? What is the right solution? We have to satisfy all the constraints.
Plus, like there should exist an edge.
No, for every edge, it is not that there should exist an edge. What is our constraint? For every edge, if you sum up, you should satisfy the constraint. Will it be satisfied with xi dash for all edges? Why? Initially, okay, for some edge, maybe there is one endpoint. I mean, can it happen that both endpoints we are rounding to 0? That is the problem, right? That edge will not be covered. Can it happen? Why not? Yeah. So, if both were less than 0.5, take an edge between say Vi and Vj. If both xi and xj got value less than 0.5, then that constraint was not satisfied, right? It is less than 1. So, for every edge it is guaranteed that in the LP solution at least one will be greater than or equal to 0.5, right? In the LP solution, it is guaranteed for every edge bi vj, either xi is greater than or equal to 0.5 or xj is greater than or equal to 0.5 or both. Therefore, after rounding, at least one of them will become 1, right? Either xi dash equal to 1 or xj dash equal to 1 or both. Okay. That means even after we round, all the constraints are satisfied. All the constraints are satisfied. So, we have a solution, though it is not an LP solution, but it is an integer solution right now. It is satisfying all the constraints, it is an integer solution, right. So, it is a solution for our ILP also. It is not an it is probably not an optimal solution. Okay. But what can you say? What is the cost of this solution xi dash compared to the cost of the LP, the real valued solution xi's? How will you compare? What is cost of rounded solution? This is sum over all I equal to 1 to n Ci xi dash. Xi dash. How will it compare with sum over all I equal to 1 to n Ci xi? We need to compare. Why?
Because xi is increased maximum by 2, maximum by 2 times.
Correct.
Otherwise it is reduced.
Correct.
So Ci's are safe.
Ci's are positive also.
It is same for both.
Correct,
Positive
correct.
And same for both.
Positive and same for both.
And same for both.
Correct. So what he is telling me is that I can say that this is in fact less than or equal to 2 times sum over all I is equal to 1 to n Ci xi. These are xi's are not necessarily integers, but this is true. Why? Because every xi dash is less than or equal to 2 times xi. Okay. Not only that, that is not sufficient, all costs are also positive. So, this inequality holds, right? Right? Because for all I, xi dash is less than or equal to 2 times xi and Ci is greater than 0, greater than or equal to 0, right? Greater than 0. So, this is true. Okay. Can I write one more line here? Can you all see it? Okay. So, this, what is this? This is my optimum. I solved it optimally, the LP. So, what this means is that sum over all I equal to 1 to n Ci xi dash is less than or equal to 2 times this thing, right? Right? And what about this side? Can I say that this is greater than or equal to? Okay, this is enough, right? Because I know that this relation is also true, right? I have this relation which says opt LP is anyway less than or equal to opt ILP. So, I can write this is less than or equal to 2 times opt ILP of the same instance, right, for the same graph, right. So, what I got is, okay, opt ILP is my minimum vertex cover value, right, that you initially agreed. if you have an integer solution that corresponds to a vertex cover, and when you have the minimum solution, minimum valued solution, that is your minimum cost vertex cover, right. The opt ILP value is your minimum cost vertex cover. It corresponds to a minimum cost vertex cover. And this is one solution which is an integer valued solution for the ILP, right. So, this is one vertex cover, and this is the you have this guarantee that it is not more than 2 times the optimum possible. So, that is the guarantee of approximation, 2-factor approximation. So, this is actually less than or equal to, this is equal to opt ILP is the optimum vertex cover value also, right, minimum cost vertex value, min cost VC of G. Okay. So, what we got is our solution that we got by rounding is less than or equal to this thing. This is equal. Okay. So, to sum it up, we did this. So, initially formulated it as an ILP, then we know that all linear programs can be solved in polytime. So, we converted it into, relaxed it into allow real solutions, solved it using any of the algorithms, known algorithms, okay. Use it as a black box. Then we obtained a solution, we converted that solution to an integer valued solution by using this method of rounding. That is, if it is half or more, a variable is half or more, we rounded it to 1, otherwise we rounded it down to 0, okay. And we told that by this rounding we are not increasing the cost much. We get a integer solution, that is one thing. It satisfies all the constraints. Now, its cost is not increasing much. It is not increasing more than 2-factor. Okay. So, we got everything. So, this is an example of using a integer linear program to obtain a approximation algorithm for minimum vertex cover. Similarly, we can do it for other problems also. Okay, so, what is the lower bound that we used here of the related problem? Earlier algorithm, we used the matching size as a lower bound. Here, what is the lower bound? We have 2 sides of an equation. So, what is our 2 sides of an inequality, 2 inequalities. So, what is the lower side?
This is greater than optimum of I.
This thing, right? Optimum of the LP, related LP is actually giving us the lower bound. We got that, our solution is correct. That is what is helping us. Okay. So, in lot of cases, this having a good lower bound of a related problem is helpful. We will use a similar method. This is your the first question in your tutorial sheet, today's tutorial sheet. Okay. So, the question, in case you do not remember, I am just reminding you. So, this is the set cover question. We also have a cost function defined, that is all. So, you are given a set of elements. So, without loss of generality, if E1, E2 to En are the elements, let us also just think that 1 to n are the elements in the universe U, and you are given some subsets, some m subsets. M can change depending on the input instance of the problem. So, there are some subsets given. So, assume that together they can cover the entire set U. If you take union of all the things, all the elements can be covered. So, the question is can you find, so that collection is capital S, script S is the collection of all subsets, some subsets given to you. Okay. You need to find from these subsets, choose a sub collection such that that is sufficient to cover all elements of the universe U. That means every element of the universe is present in at least one of the subsets which you have chosen in S dash, okay. And also there is a cost function given for every set that is given to you, subset given to you, there is a cost function also given, which is a positive cost. So you need to form this subset subcollection S dash in such a way that the total cost is minimized. So that is the objective. So first you convert this problem, formulate this as an ILP, define proper variables and convert it into an ILP, such that if you find an optimum solution for the ILP, it will represent a optimal solution for the minimum cost set cover problem. Set cover is NP hard, right? That you have seen, right? A reduction from vertex cover to set cover, right? Cost also is only a generalization. General problems are only going to be harder than the original, not going to be lesser, because if you assume everything has cost 1, it is equivalent to the version without cost given, right? Okay. So please formulate the ILP for this problem. We want to get a approximation algorithm for the min cost set cover problem, but here we are not aiming for any 2-factor or anything, because such a thing does not, it's not there unless say some assumptions, very unlikely things happen. Though there is a reduction from vertex cover to set cover is, as far as approximation is considered, it is a harder problem. For some of these problems, this LP and ILP values will be the same, okay. For some problems there will be some difference, okay. So typically we write this LP, if you ILP, if you relax, you may get better solutions, right. ILP is a constraint, so it might get lesser optimum solution, right. But for some graph, say for some problems, it can occur that both are the same, okay. So such situations also occur. Say if you, just to tell you, this is just for information. So if we are doing it later, then we will discuss in detail. So if you try to formulate maximum matching problem as an ILP, you can do that, okay, right. Then you can relax it to get a LP. So this kind of relaxations are usually called fractional problems. So fractional vertex cover, fractional set cover, we can say that the LP version of it, you can call it, it is not really a vertex cover or set cover. So you can say it is a fractional set cover, fractional vertex cover. You will think that this say 1/4 of this set is taken or something like that, right. So it is not really the combinatorial problem, it is but a related real world, real domain problem, real R, okay. So if you think of bipartite graphs, okay, if you do not think of all graphs, if you think of only bipartite graphs, then this particular LP that you are getting for maximum matching problem or minimum vertex cover problem, okay, whatever, they will have the property that these two values are the same, okay, for bipartite graphs if you take, okay. This is some property of, if you are from math, then you will see that it is because this constraint matrix has some nice property called total unimodularity, okay. So under some constraints these two values become the same, and in such situations we get sometimes it can lead to polynomial time algorithms. Say for bipartite graphs, you can find for any graph maximum matching can be found in polynomial time. Somebody had told, right, there are easy algorithms to do that. So that will also give you vertex cover solution also for bipartite graphs. This and all will follow, okay. We are not getting into it, but there are many problems for which this kind of formulations can help, and in many ways, okay. So it is useful to know this. Now I am just okay. So this factor of approximation that we are getting is here f factor, where f is the frequency of the most frequent element, right. So how bad can it be? Maybe there is some element which is present in all the m sets, so it can be even m factor, right, which is not very good. Okay. So there is also another way of obtaining an approximation algorithm for set cover. So that is that will give you a guarantee, approximation factor, which does not depend on this m. This m is number of sets, but instead it will depend only on the number of elements in the universe, the approximation factor. Okay. Here it can be as bad as m, right, if you do it this way, right. But we cannot compare both these algorithms directly, because for some algorithms, some instances, or some set cover instances, this may perform better, for some other instances the other one may perform better. So whichever is good, you can take that, right. So it is just the greedy algorithm. What should a greedy algorithm for set cover do? Okay, suppose we had no costs. Every set had cost 1. Then what does a greedy set cover algorithm do?
Choose each set one by one and check if it covers.
That is not greedy, no. And you may end up taking everything, right?
Stop when it.
What is greedy there? So maybe you will try to select a set that contains the maximum number of elements, right? That is a greedy strategy. And then you will see certain elements are covered. The next step, you will only look at the uncovered elements, and you will select a set that covers the maximum number of uncovered elements, and you repeat this, right. So this is a greedy strategy for the version without cost. Okay. If you have a cost also, then it is only a minor variation of this greedy strategy. What we can do is see which set is the most cost effective in covering elements. What is cost effectiveness of a set? Cost effectiveness is not just the minimum cost. I cannot say the minimum cost set, maybe it covers just one element, right. But another set may be having slightly higher cost, but it may be covering several elements. So cost effectiveness is something like if I spend 1 rupee, how many elements does it cover, right, something like that. Okay. So the cost effectiveness is, this is a greedy algorithm. Okay. So at any point of time, you have a certain set of elements which are covered, other elements are yet to be covered. Okay. So let C be the set of at time t. Okay. So let us call the other set U minus C as C complement. Okay. C bar equal to this set U minus C. Okay. So for covering the uncovered elements, how effective is each set? Okay. That is what we are going to define. So how will you, can you give me a formula per uncovered element that this set contains? If this set is taken, how effective what is the per cost element that you are paying? Per element cost. What is the per element cost that you are paying if you choose one particular set, say for a set Sj, cost effectiveness of Sj at time t is per element cost. In, but some elements of Sj may be already covered. Correct? So this is correct. So this is cost of, let me say C of Sj divided by number of elements in Sj. I cannot say because some elements of Sj would have been already covered, right? So I have to say Sj intersection C dash, C, right? Uncovered, for covering uncovered elements per element, what is the cost? So this is the cost effectiveness of set J in covering the remaining elements. Okay. So the greedy strategy is initially choose the most cost effective set. That the most cost effective in the sense the per cost element is the least, right? At any step keep choosing the set whose let me because it is effectiveness, okay. Whose cost effectiveness, because it is effectiveness, shall I take the reciprocal of this? Yes. It is effectiveness, no? Best effective, okay, so I will define it the other way, okay, 1 by this. So that is like Sj intersection C bar divided by cost of Sj. This is like per each rupee spent, how many elements am I covering? Okay. Right? How good am I spending my money? Okay. Whose cost effectiveness is the highest, right? Just think about it. If with 1 rupee I can take 10 elements, 10 new elements, and with for another set with 1 rupee I get only 8 elements, 8 new elements, I will take the set in which I can get 10 elements for 1 rupee, right? That way. Okay. So that is my strategy. After that, redefine the set C. C will be again repeat this. So initially the algorithm is this. So initialize C to be empty, no elements are covered till C becomes the universe, okay. Choose a set from script S such that cardinality of set Sj is that cardinality of Sj intersection C bar divided by cost of Sj is the maximum. Okay. Then C is C minus redefine C. Now the elements of Sj are also covered. So you redefine C and then repeat. Oh, okay, yes, C union Sj and repeat. Okay. So this is our algorithm. Now we want to analyze this algorithm. Okay. I want to show that, okay, this also, this problem is slightly harder than vertex cover and all. So we cannot hope to get a 2 factor here. Okay. So what I am claiming is that I can achieve a factor something like log n, where n is the number of elements in the universe. Okay. To make it precise, have you seen this function, so which is called a harmonic number, which is like Hn is defined as 1 plus 1 by 2 plus etc. plus 1 by n. What is the growth rate of this function like? Have you seen it? What might be a good approximation? Is it like growing like a constant, or is it growing like n, or it doesn't look like it grows like n, right? Actually, this is a very common exercise that is given in Corman. Maybe we can do it later as an exercise too. This you can show that, okay, can you upper bound it with an integral for math people? This is a function, you can plot it, okay. You can have an upper integral and a curve which is bounding it from above, and another curve which is bounding it from below. So I think this is like something like 1 plus log n is an upper bound or something. Okay. There may be some slight changes there, I do not exactly remember, but I think this is the thing. Okay. If we derive, we can get it exactly. Okay. I think its lower bound is also like I think this is the thing. Okay. Log n to the base e. Okay. So the claim is that this algorithm which I just described, right, this greedy algorithm, its approximation factor is at least, I mean, it cannot be worse than Hn, cannot be worse than log n, 1 plus log n. That is the claim. Okay. So here actually I am not trying to, in all the previous things we were trying to have a related problem, and we were trying to say that the related problem we somehow solve and get a solution for it and relate to this, right. But this is slightly different. Okay. We are just following a greedy approach. So we cannot rely on that related problem like approach here to get a lower bound. So instead we will directly try for a upper bound to say that the cost of the solution that we obtained this way, right. So, okay. So, choose a set Sj. I should have also told S script S dash is S dash union insert add Sj to S dash. S dash is initially empty. Okay. All these sets I am collecting. Okay, that was the entire thing. So, I have to directly do it somehow. So, how can I do it? I should compare it with the optimum value, right. My greedy solution will have a cost, right. I need to show that it is not much more than the cost of an optimum solution. So, in another ways, so what I should say is, even the optimum solution would need at least this much. If greedy needs this much, what the optimum needs is also not much less. Optimum also would need something close to what the greedy needs. That is what I am trying to do. Okay. So, you look at maybe the first element, that is okay. You will first select one set, right, to add to the set cover this way, in the greedy way. Now, let us just think of the elements being added one by one. Some of them will be added in a bunch, but just have an ordering. Just think that they are added one by one. In the same step, they are added one by one. So, if you think this way, you can order all elements in the order in which they got covered, right. Okay. So, I am going to now prove that this greedy algorithm achieves Hn factor approximation guarantee, okay, claim. Achieves Hn factor approximation guarantee. Okay. So, just number the elements, renumber, maybe if you want, renumber the elements in such a way that they are numbered according to the order in which they were covered by the sets included in the set cover, which S dash, right. When you, in the first step, you may have some 10 elements included, just call them E1 to E10. In the second step, some more elements will be covered, call them from E11 onwards, right. That is the way in which you are going to number. Order in which the elements of U got covered, covered by sets included in S dash. Okay. So, now look at the first element. So, what can you say about the price that you would have paid? So, when we are taking one set, okay, when we are taking one set, let us think that the cost we are paying is equally divided among the remaining elements, that remaining uncovered elements of the set. So, if I am choosing set 10, and it has, maybe originally it had 50 elements, but now it has only say 5 elements, right. So, for covering these 5 elements, new 5 elements, I am paying cost 10. Okay. So, per element cost, this cost 10 is divided among these 5 elements. So, I will say that price of that element is 2 rupees, 10 divided by 5. Okay. So, let price of EI is equal to cost of S divided by number of uncovered elements of S, where S is the first set chosen to S dash, script S dash, that covered this element EI. Okay. EI was covered in some step. So, what was the set that covered it? Okay. Its cost divided by its number of elements. So, this is the reciprocal of this thing actually, right, is not it? Cost of the element, cost of the set divided by this thing. Okay. So, this is the price of the element. So, if you add up the price of all elements, what will you get? Is it clear what is the price? When we are choosing a set, that time that set will have certain number of uncovered elements, and this, for taking this set I have a cost also. So, the price is per element cost at this time. Okay, that is the price. So, if you add up the price of every element, what do you get? Okay, if you add up all the price of all elements which were newly covered by S, this set S, what do you get? Cost of S, right? So, what do you get if you add up price of all the elements? Cost of? Cost of? In S dash, right. So, whatever is included in S dash, cost of all those sets, right. Agreed. Okay. So, so cost of, so if I take summation of price of EI for each EI in S, EI in U, then what I get is summation of cost of S for S belonging to S dash, right. Agreed. So, for each time I am taking something to S dash, right, that set has paid its cost, that was equally divided among its elements. I am multiplying with the number of elements when I am doing this thing, right, adding all those things. Is it clear or not? If it is not clear, I will explain one second. So, this is the claim. Suppose S had some k uncovered elements when it was chosen. So, sum of price of EI, where EI is an uncovered element of S. What is this? simple. This is cost of S only, right? It is equally divided. I am just adding this thing now for all the sets. That is how I got this. Okay. So, all elements are covered in this way. If you think every element is covered by exactly one set, uncovered. When it was uncovered, what was the set which covered it? Okay. So, every element has a set which covered it, exactly one set which covered it in that way, the first time which covered it, right, that is the owner or something, right. So, this is obvious. If you sum up price of all the elements, then you get the total cost of S. So, now I have a claim. This we do not need. I just wanted to convince you that this is the case. Okay. So, if I want to bound cost of, this is cost of solution, right. So, if I want to bound cost of the solution, I can, it is enough to bound the total price of all the elements, isn't it, because both are the same. Total price of all the elements is exactly same as price of the solution that I have chosen, set cover that I have chosen, right. So, the conclusion is cost of choosing S dash is sum of EI in the universe, price of EI. Okay. Now, I will just try to bound the price of each element. Okay. I will just make a claim, you should prove it for me. So, claim is price of EI. What is EI? We have arranged the elements now in the order in which they are covered. The element which got covered first is E1, like that. If you arrange it that way, price of EI is less than or equal to the cost of this, I will say some S star, okay, divided by n minus k minus 1, that is n minus k plus 1, where S star is the optimum, is an optimum solution. Optimum cost set cover of the given instance. This is my claim. You have, for any instance, you have an optimum set cover, right? Suppose the sets cover all the subsets together cover all the elements, otherwise reject itself, right? You do not need to consider solving the problem. If that is the case, you always have some set cover, so you have one optimum set cover. Let it be, let S star be one such optimum set cover, optimum cost set cover. So, okay, it is not K, this is I. So, the claim is that for covering ith element, when the elements are arranged in the order in which they are arranged, then the cost, the price of covering this element is only this much. Optimum way, so this is opt by opt cost, the optimum cost possible divided by n minus I plus 1, okay. So, this is my claim. So, can you prove it? Give some argument, intuitive, I mean it gives some logic why it is like that.
Cost of S will be always less than equal to cost of S star,
Cost of S, any collection that you are choosing, S dash, right?
Yeah.
S dash is some vertex cover, so optimum will be certainly less than or equal to the one that you are choosing.
Number of uncovered elements will be greater than n minus I minus 1. So then it follows.
The number of
Uncovered elements of S will be greater than equal to n minus I minus 2. So then it will follow because price of A is just the ratio.
Okay. Okay. Are you getting a reason? One person gave me a reason. So when this element was uncovered, right? There is some step in which this element got covered. In that step, can you say that at least so many elements were uncovered? This element and the remaining elements were certainly uncovered, right? How many are they? Only the previous I minus 1 elements were covered earlier, or less than that. This stage would have started, so the elements are like E1, E2 to EI, then n elements are there. So this element got covered in some step, right? Maybe the elements which got covered in this step are starting from here. So we know that at least this many uncovered elements are there. How many are they? N minus I minus 1, which is n minus I plus 1. So the number of uncovered elements at the beginning of the stage in which this element got covered is at least, I cannot say it is exactly equal to, because there may be some more, there may be, right, in the same step. So at least n minus I plus 1 elements were uncovered at the beginning of the step in which this element got covered. So does that give you a reason? Okay. So by an averaging argument, it is easy to actually, you can show it yourself that if there are this many uncovered elements, right? The optimum, right? The optimum set cover, S star, okay, it would have covered all these elements with cost opt. The total cost of S star is opt. With that much cost, it anyway covered all these n minus I plus 1 elements. Okay. Greedy, in this particular metric, greedy is better, right? It is actually reducing this per element cost. Per element uncovered, per uncovered element cost is the least for greedy, even better than S star, right? S star was globally the best. But if you consider this metric, okay, so I can say that the total cost of S star is equal to opt, right? So that means some element of S star, so has cost effectiveness or has per element price less than opt divided by n minus I plus 1. Do you agree with this? If all elements in S star had per element price greater than this value, then together they cannot have cover all the elements with opt price, right? It's just an averaging argument. Take the converse. If every element, every set in S star was bad than this average cost, their average cost was higher, then together how can they achieve an average cost of this? Their average cost is, right, the average effectiveness of these elements is actually opt by n minus I plus 1, right, for covering the uncovered elements, right. If each of them had worse per element cost, that is higher per element cost, then together they cannot achieve this per element cost. This is only an averaging argument, right. So, that means that there exists at least one element that was originally present in your S star which has cost effectiveness which is this or better, opt by n minus I plus 1 or better, not cost effectiveness, per element price is this or less, okay. Fine, agreed? No, I am not saying this. I am concentrating on the set of uncovered elements at the beginning of the stage in which EI was covered, okay. At that stage, at least n minus I plus 1 elements remain to be covered, okay. You consider all those elements which are remaining to be covered. For covering them together, S star, all the sets together in S star would have covered them with a cost opt. So, the average per element cost is opt divided by number of uncovered elements for S star, right. So, that means that at least one set in S star should be this good, right. If all the sets in S star were worse, their element price was more per element, then you cannot cover all of them together in opt, okay, right.
N minus I plus 1 are uncovered, right? So after this there might be some set which might cover many of them.
No, I am just going to argue that, so the price, so I haven't completed the argument. I only told that some element of S star, some set, not some element, some set which is present in S star has per element cost less than or equal to, not less than or equal to opt by n minus I plus 1, fine. It's an optimum collection, right. Can someone, if you want a proof, you can prove it. Okay, just the same thing what we did earlier, we will just repeat that if you want a proof for that, okay. It's not difficult at all. Suppose you have some k sets in S star, okay. S star is your optimal solution, not, we don't know how to find it, but there exists an optimal solution, okay. Some S1, S2, etc., say Sk, okay. So, so the claim is only this: if this is strictly greater than, if each set is bad, greater than op by n minus I plus 1, then S star cannot cover the remaining elements with total cost opt, which is the sum of all those sets in S star. Opt is the sum. This is easy to show. I mean, think about it. It's only a summation. What is the per element cost? It is just this thing, right? Number of cost of the set divided by number of uncovered elements. Okay. Multiply it with number of uncovered elements in that. Add it together. Then you should get cost. I mean, again the number of uncovered elements. So it is getting the same thing, right? Fine. You should get opt. Fine. So that is the only argument. Now, so the claim is that now there is a one set in S star which has cost effectiveness, which is, I mean, per element cost which is less than or equal to opt by n minus I plus 1. So we don't know opt, this S star. We are only following greedy, right? But then greedy also knows all these sets, right? If S star itself has one such set which has price like this, then if we greedily choose, we can only get better, right? We are following greedy, we don't know S star, anything about S star. But that set exists in the collection given, right? So, therefore, there exists some set in this collection S such that if we use it to cover, if we add it now, to S dash, say let me call this as some S tilde, small s tilde, price of EI will be less than or equal to opt by n minus I plus 1. Is this okay? Just think about it, ask me if you have any questions. What I am saying is greedy in this particular aspect, that is price per element, right? This aspect greedy is the best, right? That is not probably the best way to do it, but greedy is the best in this strategy. So even in the optimum solution, you have one set which has opt divided by n minus I plus 1 as the price per element. This set exists in S star. So this set exists in the given collection to you, right? Greedy can choose that one or anything better than that, right? Greedy will not choose anything worse. When this is there, price per element, if you choose this, you will get at least this good, right? You need not take anything worse now, you can take this. So the price of covering EI is going to be the set that you have included, which may not be the same set. Where did I? Some set, say small s of S star has price this, so you can choose this S or anything better, right? So you are never going to pay more than this price, per element for covering EI. So, what is the total cost now? We initially told that the total cost of S dash is just the sum of prices of all the elements. So, what is that? Sum overall I is equal to 1 to n price of EI. So, do you get that factor now? Hn. So, what is the total cost now? So, cost of S dash is sum of E I in U, price of EI. Price of EI we know, we have a bound now, which is less than or equal to opt, that is the total price of S star, which is imaginary. There exists something, we do not know how to find it, but it is true. What will you get if you take this summation? Take opt out and sum. So, this is equal to opt into 1 by n plus 1 by n minus 1 plus etc. plus 1, right. So, this is the summation, which is Hn. Okay. Fine. So, this shows that okay, we did not have any related problem and all, but we can, though we do not know how to find an optimum solution, we know that there is an optimum solution. So, we can compare with whatever was the optimum cost and say that if optimum cost was this much, we are not paying much more than that. The factor by which we are paying more is only 1 plus log n. It is not 2, we cannot hope to get it. Okay, it is known that this problem is hard, even not 2 factor and all is not expected. I am not giving you a proof or anything, but I am not saying it cannot be done better also, I mean, because we have not proved it, but we can get a greedy solution for which the approximation factor is 1 plus log n, or in the worst case it is only going to be 1 plus log n. So, just think about the whole thing and see if you have understood it or you need more explanation. You are trying to minimize the per element cost that you are paying at any point of time. And if you arrange the elements in the order in which they got covered, we are saying that the per element cost is, for covering element I, its cost is not going to be more than opt divided by n minus I plus 1. So, if you add this up together, you get it. That is the entire idea. Okay.